Hello, everybody. If you recall, we started chapter 4 by thinking of and solving certain application problems called related rates. Okay, so in this section 4.7, we are going to solve another type of well-known calculus problems. And these are called optimization problems. Basically, it's finding maximum and minimum of functions. And as you can imagine, again, this is quite important because, again, we try to optimize things. We try to maximize profits. We try to maximize areas. We try to maximize volumes and minimize cost and so on. So there is a huge number of application problems, and we will look into a few of those in section 4.7. Okay, so the word optimization basically means to optimize, which means to find the best or the highest or the greatest, okay? And so we have studied these functions where we could find absolute maximum or relative maximum in this case, and relative minimum, or we call them local maximum and local minimum, all right? So clearly, this is an important process in applications because we want to find maximum and minimum points in real life situations. So now we want to find max and min. What do you want to maximize? Profits, volumes, areas, and things like that. You want to minimize maybe the cost, expenses, the loss and damages and so on. So we want to find max and minimum in real life situations. All right, so let's go ahead and do that. The word optimize again means to find the best. And so we want to model a function, and then we try to solve to find the best and the highest or the lowest point of a function. All right, so I'm going to give you one example first. And then based on that example, I will give you some general guidelines to follow, okay? Now, again, there are all sorts of different types of problems within the what we call optimization problems. So the variety is vast. And for each problem, of course, you have to set it up in different ways. And so there's no one general formula, like the product rule. You just have to find sort of a general ways to identify the problem and to solve and find the answer. Okay, so let me just give you this first example. This kind of example, by the way, is found again in every calculus problem. Okay, so calculus book is really not a calculus problem unless you have an optimization problem where you try to maximize the area of a garden. Okay, so here's the situation. Let's say you have this property by some body of water. Maybe you have a river or a lake or something, and you want to enclose a rectangular region. This sounds so calculusy. Okay, so you have this rectangular region, and of course you only have to have a fence 3 sides of it. Okay, and so because it's a rectangle, you have x and y. X is the width and y is the length. All right, so this is a rectangular garden to be enclosed on 3 sides. With 3 sides, find, or the problem would say find the maximum area, or in our language we'll say maximize the area. Now, of course, you can make it bigger and bigger if you just get x and y to be very, very large numbers. Let's say x is like 15 miles and y is 30 miles. Well, so you have to have some restriction, of course, to solve a problem. And in real life, you have restrictions, and these are called constraints. Okay, so let's say the constraint here is with 100 feet of fencing. That's all you have. Okay, now, of course, when I say fencing, I'm talking about this x side and y side and x side combined. These 3 sides require fencing, and the total fencing length should be 100 feet. So you can't make a really big garden here. It's just talking about a small, relatively small garden. All right, so the strategy actually calls for and later we'll discuss this more generally, but identify two things. Okay, number one, a function to be maximized or minimized. So let's just call them a function to be optimized. Okay, and in this case, you know what that thing is. It's the area. Okay, the area function is, of course, x times y, right? Because that's the area of a rectangle, x by y, dimensions x and y, in this case, x and y feet. All right. The other thing you have to identify is what I was just talking about. Technically, it's called a constraint. Sometimes you have more than one, so you have constraints, and that is 100 feet of fencing. Now, how do you write that? Well, I mean, it's pretty easy in this case. You have x, the side x, and side y and side x. So it's x plus y, or 2x plus y, has to be 100, or actually less than or equal to, but here it says 100 feet of fencing. So let's just use all of it, okay, since we are trying to maximize the area. So we are trying to, and here's the language we will use. We are trying to maximize the area xy subject to the constraint 2x plus y is equal to 100. All right, so what we do to solve this problem is to write the function to be maximized. Now, unfortunately, right at this point, you have two variables, okay? We have not learned, and in Calculus 1, we will not learn how to maximize a multivariable function. So you have to write this in terms of just one variable. Let's use x or y only, but not both. And how can we do that? Well, that's where the constraint comes from, right? So the constraint tells me that y is negative 2x plus 100. All I'm really doing is to solve for y in terms of x. This easily gives us y is equal to negative 2x plus 100. So then we substitute that. And when you do this, now watch, a becomes x times this new y, right? So this is completely now a function of x. So I'm going to write a of x, right? So this to be maximized. Okay, so I have used the constraint. So I know this is pretty much all the information I am given. So now we take the derivative of a. You can write this as dA dx or a prime of x. Oh, actually, let's go ahead and rewrite this in a more traditional way. It's negative 2x squared plus 100. Okay. And at this point, you recognize this as a quadratic function. And as such, you know this is an upside down parabola. There is a way to find the maximum without using calculus. Maybe you learned that in an algebra class. The axis of symmetry, the vertex happens when x is equal to what, negative b over 2a or something, right? But if you use calculus, it's a lot easier. Negative 4x plus 100. You set this equal to 0 because you want to find the critical point. X is 25. Okay. Now, of course, you know, we don't know. We found a critical point, but remember, a critical point, what happens at a critical point to a function? It could have a local minimum, it could have a local maximum, and it could be neither, right? So we have to sort of investigate the shape of the graph. Shape of the graph, that sounds familiar. Yes, that's exactly what we were looking at earlier in the chapter. But what do you know about this function? Well, when x is 25, it is the maximum. Well, how do you know that? Well, because you know that this is an upside down parabola. And in fact, you know from this equation, a0 is 0, right? Now, let's think about the domain. Can x be 0 or negative? Now, in realistic terms, x can't be 0 or negative, right? I mean, if x is 0, it is sort of allowed. You just don't have a rectangular garden. You just have a straight, you know, line of fencing along the river and no garden. So at this point, you could maybe say x, you want x to be greater than or equal to 0. Now, you could exclude 0, but in order to find the maximum, you know, absolute maximum and absolute minimum, it's nice to have a closed and bounded interval. So let's allow x to be 0, even though that would be ridiculous because you would not have a rectangular region. And then how big can x be? See, if x is 50, and then this side is 50, then you have just used all 100 feet of fencing, right? So y can be 0, but then again, this is not a rectangular region, right? X could be 49, X could be 49.9, Y would be extremely, extremely small. But so let's let X be up to 50. So again, you don't want X to be exactly 50, but you can get this to be as close to 50 as you want. Although the garden would look very, very narrow in that case. All right, so with that, you know that what's A of 50, by the way? That's pretty clear. If you have 50 here, y is going to be 0. So that's going to be 0, right? So you have this 0 here and 0 here. It's a parabola, upside down parabola. So you know the function is going to look like this. And so you know this is a point of a maximum where the maximum occurs. All right, so F or A has its maximum at 25. And in fact, you know it is an absolute maximum because this is the only critical point. And if you check at the boundary points, A of 0 is 0 and A of 50 is 0. So it is a maximum point. And so you can say A has its maximum at 25, or I should say X is equal to 25, in this case, feet. All right, what's going to be the Y value at this point? Well, we plug that in, so it's -2 times 25 plus 100, and that's 50. So you say A is maximum when X is 25 feet and Y is 50 feet. Let's try to find that maximum area. You can use, well, you can use this formula, 25 by 50, or you can use this formula, X is X times -2X plus 100. That's going to give you the same thing. It's 25 times 50. And that's 1,250. You can say unit squared if you like. In this case, that unit is specifically given as feet. So this is square feet. Okay, so you can make a garden as big as 1,250 square feet by using the 100 feet of fencing. So that's not too bad, right? Now, of course, some problems may be harder than this, but let's go back and review what we did. In all of these optimization problems, okay, you will see that there is a function to be optimized. Now, you need to find it. Sometimes that is a tricky situation. It may not be as easy as the area of a rectangle. It could be the volume, and you may have more than 2 variables. In this case, you had 2 variables, X and Y, and you wrote one in terms of the other. You may have to do extra work before you can come up with that function to be optimized. And there's a constraint. And the process of making this as a function of one variable, like this one here, that process requires you to cleverly, smartly, efficiently, intelligently, mathematically use the constraint or constraints so that you can make that function to be a function of one variable. All right, so that's pretty much what you have to do. So maybe I can just say a guideline. Number 1, identify the quantity or function. Now it's a quantity, but of course we use functions to represent quantities. So we use identify the quantity to maximize or minimize. All right, and then number 2, use constraints. Maybe one constraints. Use constraints so that the function to be maximized or minimized has only one variable. and then you differentiate it. Okay, and at the same time, you may want to, when you do this, you may want to consider the domain, okay? Because many times in real life, not in the abstract mathematical world, but in the real life, many quantities should be positive, or at least not negative, all right? So with that in mind, let's go to the second problem, another very well-known problem, okay? The open box problem, which inserts itself into every calculus problem, calculus book. All right, so this is an open box. What we are trying to do is to maximize the volume of a box that you construct from a piece of paper or a piece of metal or something. All right, so let's say you start with a rectangular cardboard or metal, okay, or whatever. So let's say this is 8 by 10 inches, 8 inches by 10 inches, right? And what you do is you cut the four corners. Sounds familiar? Okay. All right, so you cut four corners, and let's say these are X by X, X inches by X inches. You cut that, and then you bend this cardboard on these four sides, and when you do so, you're going to come up with a open box. So like this. Like that, right? See, these appear in so many times. I have taught this class so many times. These are easy to draw now. It looks sort of real. Okay, now remember the outside, you have, how many sides do you have? You have 5 sides. You have the 4 sides on the side, around this, and then 1 on the bottom, but not on the top, which is why this is called an open box. All right, so the question is, let's say you start with a 8 by 10. 8 by 10, 8 inches by 10 inches of cardboard to construct an open box. All right, and we want to maximize the volume. Okay, so this is not as simple as the other one. Area is not X times Y. We don't even have Y at this point yet. All right, so how do you do that? Okay, so first, let's try to find the volume. Okay, at this point, this is all it's given to you typically in the problem. Right? We have to figure out the dimensions of this box. Right? So what is this box? So this first edge here, the width is actually here, right? And so this, you start with 8 and you take out X and X. So this is 8 minus 2X inches, right? Similarly, this length of this open box is this side, which is you start with 10 and subtract X and X. So this is 10 minus 2X. Not too hard, right? What's the height of this? The height is exactly this, which is just X. All right, so the volume, which is the function to be maximized or quantity to be maximized, is 10 minus X squared, 8 minus X squared times X. Okay, it's basically the length, or width times the length times the height. Of course, I can simplify this. But before we go any further, let's think of the domain of this function. X, of course, can't be negative. Now, X can't really be 0 because then you wouldn't have an open box. But the point is, you can make X really, really close to 0, right? If you want to, you can make X to be 0.001 or something, and then you have a very shallow box. And that's not going to maximize the volume because of its shallowness, right? But it's possible for X to be arbitrarily close to 0. So let's just assume that X can be 0 so that we have a closed and bounded interval. Now, how big can X be? Right? If X is 3, that's okay. But if X is 4, you have 4 here and 4 here, and there is no box left because this whole side is 8. Okay, so X can't be bigger than 4. Now, if X is 4, once again, you don't have an open box. You just have a flat or flattened open box. But again, to have a closed and bounded set, let's just let x be between 0 and 4 with those two endpoints included. All right, now I only have x, so I don't really have to rewrite this. You know, I don't have to write y in terms of x or anything. But because it is a product of three things, let's just go ahead and multiply. So you have 80, that's this, minus 20x minus 16x, that's minus 36x. And then you have plus 2x times 2x, that's 4x squared. And this entire thing should be multiplied by x. So what we have here in the standard descending order is going to be, oh, sorry, it's 1x. 4x cubed minus 36x squared plus 80x. This is to be maximized. Right, now the constraints are already embedded in here because we started with 8 and then 8 by 10 cardboard. So this is really all you need for this problem, okay, before you take the derivative. All right, and then when you take the derivative, oh, by the way, this is a, what kind of a function is this? It's cubic. The leading coefficient is 4, which is positive. So you can expect the graph to go like this. Okay. Now I don't know where, you know, x is 0 and so on. And so that's yet to be seen. But let's go ahead and differentiate this so we can identify the critical points. This is 12x squared minus 72x plus 80. You want to set this equal to 0. Okay, well, you can simplify this maybe. Divide everything by 4, 3x squared minus 18x plus 20 is equal to 0, just dividing this by 4. All right, so you can try to factor this. After a while, you realize you really can't factor this very neatly, but you have this all-powerful tool that's referred to as the quadratic equation, right? Any degree 2 polynomial can be solved, and you can find the those two roots, two answers, sometimes complex, sometimes real, but you can find them, right? And that wonderful equation is negative b plus or minus the square root of b squared minus 4ac, and let's hope the discriminant, which is the quantity inside of the radical, is positive, because if it's negative, then you don't have real answers. And then the denominator is 2 times a, right? Okay, so this is 18 plus or minus, and you can take your calculator out. The inside is going to be 18 squared minus 240. That's 84. Okay, so that's 18, and you can factor out 4, and that's going to be 21. Right, this part, I'm sure you can do that. All right, so this turns out to be 3 plus or minus square root of 21 over 3. Now you can go ahead and take your calculator and do square root of 21. Did I say square root of 23? I meant square root of 21 divided by 3. So you can take that and calculate it, add 3 to it, and you get 4.5275 when you use the plus sign. When you use the negative sign, 3 minus this quantity is going to give you 1.4724. Okay, and these are approximate numbers, of course, because these are irrational numbers. Well, we said x needs to be between 0 and 4. So we actually don't need this. All right. And the function looks like this, right? Or it should look like this. And so this must be where the first solution is. And this must be where the second solution is, because, well, I mean, the bigger solution is, because this is, bigger to the right. And so the function is probably going to be something like this. All right, now, can you sketch this, perhaps? Okay. Oh, yeah, so this is, according to this picture, the graph has to go like this, right up, going down to the left, And so you should have a local maximum here, local minimum here. And since I have two critical points, those local max and local minimum, these two local extrema must be corresponding to these numbers. And so the local max happens here. Now, of course, you can analyze this carefully, more carefully, by using the first or the second derivative test. But I don't think it's necessary to do that because you already know the graph of this function looks like this. It's a a third degree polynomial. All right, so what does, well, let's take a look at this a little more carefully. Now, I chose these numbers 0 and 4 because something ridiculous happens, right? The flattened open box. When x is equal to 0, clearly this is going to make the volume 0. And when x is equal to 4, clearly this is going to make it 0. All right. So the more accurate, oops. Yeah, let me go ahead and draw a graph of this. All right, so I paused my recording for a little bit so I can write these things in here and then draw my axes. All right, so A is going to look like this. A of 0 is 0, as I said. A of 4 is 0. Sorry. And that's really, those are the endpoints, right? And when x is 1.47 something, so that would be somewhere around here. Okay, then the value of the function is like 50 something, right? So I'm just going to randomly pick this point to be 52.5. Of course, x and y are not on the same scale. And so what's going on here? Well, this has its highest point, as I said, and it's a cubic function. So the function will go like this, and the concavity actually never changes as it goes down to infinity, negative infinity. And then what else do we know? This is 0, and then after this, when x is 4.752, it achieves its minimum, right? So we know the function is going to start to go down this way, and perhaps you may have another point of inflection, one point of inflection here, only one, and then goes through 40 and goes to its local max minimum, and then starts to go up. Okay, again, we don't worry about this last part. This is the only part we are talking about, from 0 to 4. And so in this interval, this is the maximum point. And so we say that the area, the maximum area, is approximately, I'm sorry, it's not the area, is it? It's a, oh, why am I using A, by the way? It should all be V, okay, because we're talking about volume. And we call it capital V. The maximum volume is about 52.51, approximately 52.51, and it's a unit square. And in this case, I think we used inches. So this is going to be not square, cubic inches, with x equals 1.47, approximately 1.47 inch. Okay, so by letting that, so what you do is you cut a square whose side lengths are 1.47 from each of these four corners, and then construct this open box, and that open box has the maximum possible volume of about 52.5 cubic inches. And you cannot possibly make this open box any bigger. And that, how do you know you cannot make this bigger than 52.51 cubic inches? Because of all the work here, the calculus is telling us that is the maximum possible volume obtained from this cardboard box. And you can say that with confidence. And if you work on this problem tomorrow or next year, the answer will still be the same. Okay, and that's, again, the confidence you can have by knowing your math well. All right, I'm going to work on a couple of more problems, and that's going to be in the second part of this video.